In this video, we're going to discuss the vapor pressure. So while we've discussed the idea of phase change from going to liquid to gas, we don't have to boil something for that to happen. Like things evaporate, water dries out of clothes as you leave them outside in the summer sun. You by no means got up to 100 degrees Celsius outside, even if you lived somewhere like Arizona. So how does this work? What is going on that water is turning into a gas despite not being at the phase change temperature? Well, this harkens back to the idea that phase changes are equilibrium. And even if you're not at the phase change temperature, there's still an equilibrium process occurring. When we have a container of liquid molecules, water spread out here, well, there's a distribution of energy. And even if it's mostly on the lower end, it never really reaches zero on the high end. There's always some very small percentage of your particles that have really high energy. Well, if we think about vaporization, there is some energy that represents the energy of vaporization, that delta H of vaporization. For a mole of water, that's 40.7 kilojoules of energy. Well, you do it molecule by molecule, however, so each individual molecule needs significantly less, and the chances are there's a few molecules at any given moment that have that much energy. Now, if that happens to be down at the bottom, it moves a couple nanometers, hits another molecule, and transfers some of that energy. But eventually, by random chance, one of the molecules at the surface is going to get bumped by enough other things, all about the same time, that it's going to just launch, and it's going to go into the gas phase. Even if you are significantly below the boiling point overall, there's always a few molecules that do have enough energy to vaporize. They also need to be in the right location, moving in the right direction, but this still happens. At any given moment, when you're looking at a cup full of water, some of its molecules are turning into gas. Now, if you're outside and you're letting things dry in the sun, over time, these escape and drift away. Your material stays warm because of the outside environment, and another one eventually drifts away, and bit by bit, you will have all your water flow away. This is how something evaporates. On the other hand, if you've got a sealed container, well, that gas can't flow away. Instead, it just floats above the container. And maybe another one breaks free over time, but eventually as these bounce around, it might get stuck back in the liquid. There is a rate of leaving, but there's also a rate of return. This is based on how many gas molecules there are. One particle is going to bounce around for a while and eventually stick. But if you have 2 or 3, then at any given moment, you have 2 or 3 times more chances that it might go back to the liquid. And so eventually, well, you start with a little return with one particle and get a little more when there's 2 and a little more when there's 3 and 4. Eventually, you build up enough particles in the gas phase that your return rate is the same as your leaving rate, whatever number per second that might be. Once that happens, well, I have a volume. There's some headspace there. I have a certain number of moles. They're going to be at whatever the temperature is at, which means I have moles, I have volume, I have temperature. There's going to be a pressure associated. Those particles are bouncing into the walls. That pressure, that is the vapor pressure. Literally the pressure caused by the gaseous component, the vapor. There's some amount of pressure that this will create. And this is actually temperature dependent. Regardless if you had a bigger container or a smaller one, because that would also change how long it takes the particles to return, it's always about when those rates are equal. And those rates will be equal when that pressure is the same for the same temp, regardless of the size and nature of the container. Which means we can make nice tables, which is what we have over here. Depending on your temperature, there will be a pressure for that liquid in the gas space above it. For water, we have a set of temperatures here. Standard room temp about 23 or 25, you're looking at 21 or 24 torr. So not a huge amount. Standard atmospheric pressure, 760 torr. This is significantly less. However, as your temp goes up, we'll see that our pressure goes up, and it eventually gets quite quick. Early changes are small, later changes are large. Our early distribution at low temps has very few things with high energy, but as our temperature goes up, more and more of our particles will have higher and higher energy. The way this tends to look for the data, if we have temp versus vapor pressure, is that it curves up quite strongly. Changes aren't very large early on, but as your temperature gets greater, the changes become more drastic. And eventually, at our boiling point, our vapor pressure is equal to the external pressure. This is actually what defines the boiling point. When your vapor pressure has enough pressure to push back against the atmosphere trying to compress your liquid, it is able to freely expand and turn into a gas. And this is how your liquid boils away. So imagine this container, but we've got an outside atmosphere impacting, crushing, and pressing it down. Normally some pressure is able to escape, but at the point where your liquid is pushing out with 760 torr of pressure, which is what the atmosphere is pushing down with, any extra energy allows your liquid to expand against the atmosphere completely. It pushes back, and your volume can enlarge and just turn into a gas. This is why at higher elevations, when the pressure is lower outside, liquids will boil at lower temperatures. This is a common method for removing liquids in research settings. A Rotovap is a device that pulls a vacuum on a liquid while keeping it at a set temperature. As the outside pressure decreases, that means the pressure needed in order to boil becomes less, and it is possible to fairly easily boil things at 40 degrees if you can reduce the external pressure down to 55 torr. Pretty easy for most vacuum systems. So vapor pressure is kind of underlying what's going on in phase changes. It's always happening a little bit because some of the particles will always have the energy necessary to go through that change. At any given temperature, what you will reach equilibrium at is set for that type of material. At 21 degrees Celsius, there will always be 18.7 pressure of water vapor once it reaches equilibrium. You have to give it time. This works best in closed systems where equilibrium can be easily obtained. Outside in the regular world, because air can move quite freely, different weather patterns bring cold, dry air or wet, warm air from different parts of the planet. This is not really stable, and it's harder to reach these equilibrium, and is why we have weather. But inside, say, a water bottle that's been sitting for a while, and you'll notice some condensation drops on the sides, this is how those form. The gas can start to condense on the surface, more will replace the vapor in the air that had gone to make those droplets. It's a back and forth, but you can build up droplets in other parts of the bottle because there's a constant back and forth between going into the gas phase and going into the liquid. There's no reason it can't make a new liquid phase on part of the bottle. This also helps us tie into the boiling point and understand why the boiling point of water changes at different elevations, why that temperature is actually dependent on the external pressure. We'll dive more into these calculations in our next video.